In the first lecture of this series, I gave you the picture of the physical sciences which obtained in 1930. In 1930, with just three fundamental particles, electrons, protons and neutrons, and with just one type of force, the electrical force, one seems to have synthesized most science. There were, however, yawning gaps in our knowledge. I said earlier that the nuclear core of every atom contains about equal numbers of protons and neutrons. A neutron is a chunk of matter as heavy as a proton, but with no electrical charge, and therefore no electrical attraction or repulsion. The question arose, what is the neutron's role in the scheme of things? What holds a nucleus together? Since 1930, physics, and since 1945, unfortunately, the rest of humanity, have been occupied with the nuclear problem. The world of the nucleus revealed a new, a completely unexpected richness, a richness in concept and in fact. Since 1930, one has discovered that although all known stable atoms we had encountered in nature consisted of just the three fundamental particles I have mentioned before, there do exist other companion particles, companions to the protons, to the neutrons, and to the electrons, as fundamental, as elementary as these three. It's the story of these newer entities and the domain of phenomena that they have revealed which will be my major concern from now on. I have called these newer particles companion particles. It's important to realize that the new objects were not discovered by the classical procedure of subdivision of protons, neutrons, or electrons. The principle of divisibility, which took us from ordinary bulk matter to atoms and then from atoms to protons, no longer functions anymore. With electrons, protons, and neutrons, and the newer particles, one seems to have reached the limits of divisibility. This is something completely new in human experience. If I take an analogy of these particles to a brick thrown against a wall, it's not that the brick fragments into still smaller pieces. For the first time it appears as if we are receiving back 5 or 6 whole bricks, identically alike to the first that was thrown. One has definitely reached the end of the line of divisibility. One is at a level of comprehension quite different from any that has ever gone before. But before I describe these particles, their interactions, their interrelations, and the concepts associated with them, I would like to spend some time, in fact the whole of today's lecture, to review some of the basic concepts of modern physics, concepts to which I shall be referring again and again during these lectures. Unfortunately, these concepts are not easy, and I shall need all your patience before I hope that they become a little clearer. The first concepts I shall need are the classical ones of energy and momentum. Momentum is the amount of motion possessed by a body when it's moving. In mathematical language, it's simply the product of the velocity and the mass of the body. Similar to the concept of momentum is another concept, the concept of spin. If an object is rotating around an axis, a spinning cricket ball for example, we say it possesses spin or angular momentum. The faster an object rotates, the larger is the angular momentum carried by it. Now there's a very important law of classical physics which states that the amount of momentum or spin of a body tends to remain constant unless there are external forces tending to stop the motion or the spin. A spinning flywheel will go on spinning forever if there is no friction of its bearings. A bullet fired from a gun or an arrow shot into space will go on moving forever in a straight line if there is no air friction to stop their motion. Perhaps this great law of classical physics is completely obvious to you in the present satellite age, but it certainly was not obvious to Aristotle nor to Ibn Sina, for it seems quite contrary to the common experience of mankind. If we roll a ball on a table, one's common experience is that sooner or later it comes to a standstill. One might assume, and this is in fact what Aristotle did, that the natural tendency of a moving object is to stop, that things need some force to keep them moving. It took the genius of Galileo and Newton to contradict Aristotle. They asserted that a moving object has the natural tendency to persist in its motion. One should not look for an agency which keeps it moving. One should rather look for an agency which is likely to stop it. This was a tremendous revolution in human thought. It was this bold assertion of Galileo and Newton which was the beginning of the science of mechanics. This intrinsic persistence to go on moving or spinning is called inertia. Just plain laziness, if you like, of things to go on doing what they have been doing. Technically, we call these laws the laws of conservation of momentum and conservation of angular momentum. Now, the conservation laws have been tested millions of times under controlled conditions. When I say controlled conditions, all I mean is that one has attempted to eliminate extraneous forces like friction very scrupulously. These laws represent an ultimate truth, the distillation of our physical experience. But is there something deep that we can infer from these? Or do we have to accept these as obstinate facts which must be incorporated in any description we make of nature? Now it happens that for the conservation laws of momentum and angular momentum, one can find a correlation of these to something deeper, something more profound, something much more basic. By a process of mathematical reasoning, which I shall not go into, Dirac, whom I mentioned in my first lecture, and the great Hungarian physicist Wigner were able to show that this tendency to persist in motion in a straight line, this conservation of momentum, can actually be inferred as a basic law of nature, provided we assume that the results of a physical experiment are independent of where in space the experiment is performed. Not many of us, I do not think, have ever stopped to ask ourselves the question, do a proton and an electron on the planet Mars attract each other with the same force as they do on Earth? Once the question is formulated, I am sure most of us would instinctively say, Yes, of course. Why should the force not be the same? It would be an intolerable complication in the scheme of nature if the laws of physics depended on one's location in the universe. But what's the proof of this assertion? Dirac and Wigner stated that the proof lies in the conservation of momentum. If we can verify the property of persistence of motion in a straight line, we can be sure that the basic laws of physics are the same all over the universe. Personally, I have lived with this reasoning of Wigner and Dirac, a reasoning which connects things so distinct, so disparate, a reasoning which connects the symmetry of the overall universe with a conservation law in the laboratory, a reasoning at once so abstract and yet so concrete. I have lived with it for about 16 years, but I still marvel at its boldness, at its audacity, and its sweep. It's certainly one of the most powerful things that I know of. So much for classical physics and the symmetries of the overall universe which it seems to reveal. And remember, it's these symmetries which I am after. Now, the second discipline which I shall make frequent reference to is Einstein's theory of relativity. There are few subjects in physics which have aroused such strong misconceptions, and the reason for this is not difficult to find. Relativity theory makes statements about time strictly within a context used by the physicist. Unfortunately, the word time is also used by the professional philosopher with a very different connotation. The misconceptions arose when the philosopher started to interpret Einstein's work in his own way, sometimes even asserting that if one reflected long enough, the theory was completely obvious a priori. Let me state it categorically. There is nothing a priori about relativity. Relativity is based on a remarkable, on a far-reaching, on an astonishing experiment, whose result would never have been conjectured before the experiment was performed. The experiment is the following. If you take a lamp and measure the velocity of light which it emits, you get a certain value. More precisely, you discover that the velocity in vacuum is 186,000 miles per second. Now move the lamp as fast as you possibly can. Naively, one might imagine that the light velocity will differ depending on whether the lamp is moving or not. When the experiment was actually performed towards the end of the last century by Michelson and Morley, they found that there was no difference whatsoever. The velocity of light is exactly the same, whether the source of light moves or not. Not only that, the velocity also remains unchanged, irrespective of what the observer may be doing. One may start running away from the light source with a speed even as fast as that of light itself. Any normal, sane person would expect that if one is running away with that speed, that light will never catch up with the observer. But astonishingly enough, one would be wrong again. The velocity of light will remain the same as before. As I said before, this is astounding. This is unexpected. There is nothing a priori about it. But these were the facts, and they just had to be incorporated into physics. Einstein's profound analysis did just that. Einstein expressed the results of his analysis in some spectacular language. He stated that the resolution of the paradox lay in the relative character of time. And when he used the word time, it was in the sense of certain mathematical equations. I shall not try to go deeper into this mathematical aspect. For my purposes, the crucial content of relativity is just the following. From the constancy of light velocity, Einstein deduced that matter and energy must be identical. To illustrate, Einstein asserted that a lamp shade, for example, which is absorbing the energy of light radiation, must get heavier, the absorbed light manifesting itself as an increase in the matter content, in the inertia of the lamp shade. The radio transmitters of Radio Pakistan, pouring electrical energy into space, are progressively diminishing in their matter content. Luckily, these transmitters are also being replenished. They are receiving energy from the electrical mains. But one might really worry about the sun, for the sun is certainly getting progressively lighter because it's pouring out heat and light energy. The sun is losing weight. These statements can be and have been verified hundreds of times in the laboratories. So much for relativity theory. The third set of concepts I shall have occasion to refer to are the concepts of quantum theory. Quantum theory, like relativity, began in the early part of this century with certain experiments whose results one would never have credited. So obstinately contrary are they to anything one had apprehended before. Quantum theory asserts that there are in nature certain fundamental units, and that a number of physical quantities can exist only as integer multiples of these basic units. One simple example is the quantization of electric charge. A proton is some 2,000 times as heavy as an electron, but both carry the same quantity of electric charge. All charges in nature exist as integer multiples of this one fundamental units. Take another example. I have spoken before of spin, of angular momentum. Recall that this is the amount of rotation possessed by a given object. One would never have believed that one cannot impart an arbitrary amount of spin, for example, to a cricket ball. Yet this is precisely what quantum theory asserts. It's impossible to find in nature a spinning object, a top, a cricket ball, whose spin will not be a half-integer multiple of a basic unit discovered by Planck. One may encounter spin values half of Planck's unit, or 1 Planck unit, or 2 Planck units, but never 1.3 or 2.7 or 2.67 times the Planck basic value. Somehow, for quantum theory, integers, or at worst half-integer multiples of a basic unit are sacred, are inviolate. And as I said before, if the theory did not have the sanction of precise experiment, one would never have believed it. To take one more example, would anyone believe that the energy carried by the radio waves, or a light ray, or a heat radiation can exist only in integer multiples of a certain basic unit, in discrete, countable chunks, that energy is quantized. Again, if we did not know that this was true by repeated experimentation, one would hardly believe it. In the case of electrical radiation, one has designated this basic unit of energy as a photon, and I would like you to remember the word photon. A beam of light or a beam of X-rays in this quantum view then consists of nothing but a stream of photons, all photons traveling with the velocity of light. Let me now recapitulate. On the basis of what we know, we believe that the universe, the space-time we live in, is endowed with certain symmetry properties, with certain characteristics. We understand the origin of some of these characteristics. Others we are forced to accept at present as empirical facts, and leave perhaps for our successors in the 21st or the 22nd centuries to find the deeper basis of. We know empirically that there are certain conservation laws, laws which assert that certain properties persist. We believe we can find a deeper significance for these laws in the sense that we can correlate them with the properties of space and time. From conservation of momentum, one may infer that space is location symmetric. From conservation of energy, we may infer that the results of an experiment do not differ with the epochs of time at which the experiment is performed, that the electron and the proton will attract each other with the same force today as they did yesterday and will tomorrow. From relativity experiments, we know that the velocity of light has astonishing properties, that it's an invariant, that it's unchanging, irrespective of the motion of the light source or the movement of the observer. We accept this as something which we must incorporate in our fundamental description of nature. Once we do this, we can make the inference that all energy possesses inertia, and vice versa. Then again, experiment has forced us to accept quantum theory. We know that we can never impart spin to an object which is not an integer or at worst a half-integer multiple of a basic unit given by Planck. We know that the energy of electromagnetic radiation can exist only in discrete quantum units, the so-called photons. We find this utterly astonishing. We do not know why some physical quantities should be quantized. Perhaps this is connected with the topological structure of space and time, but we do not know. This again is a problem for the fortunate few of 100 years after. All we can do at present is to incorporate these facts within the formalism that we use, and this we have learned to do.